Should we start? Hello? You can hear me? Yes? Thank you. Should we start? Then, good morning. And so today we are going to speak about subgradients and supergradients. But similarly as yesterday that we were talking about quasi-convex and quasi-concave functions, and I said, no, I will just mention quasi-convex functions because quasi-concavity means just reversing the sign. Here is the same. Moving from subgradients to supergradients is just changing signs. I will not insist on that too much. Motivation of subgradients. The motivation is that convex function need not be differentiable. But suppose it is differentiable. So suppose we have an open convex subset of Rn and a real valued function defined on C, which is differentiable. Everywhere on C. Then what characterizes convexity is the following property. For every 2 points, let's say x bar x in C, one has f of x greater than or equal to f of x bar plus inner product, the gradient of f at x bar, comma, x minus x bar. Okay, this is just saying that the tangent line is below, or the tangent hyperplane in general is below the graph of the function everywhere. It's not difficult to prove this equivalence. I mean, if you're interested, I can give you a proof, but let's start accepting this characterization. But what about the situation in which the function is not differentiable? There may be other lines, like the tangent line in the differentiable case, which have the same property as the one defined by the gradient, namely that all the line is below the graph of the function and coincides with the function at the given point. This is the idea. So this suggests the following definition. So suppose we have a function, we have a subset of Rn. I'm not assuming anything for the time being on C. It's any subset, non-empty if you want. Then we have an extended real valued function on C. I'm assuming nothing about this function for the moment. And suppose we have an element x bar in the so-called effective domain of the function. The effective domain, denoted like this, is by definition the preimage of the reals, that is the set of points where the function takes a finite value. If you prefer, the set of points in C such that f of x is less than plus infinity. Okay. But, I mean, even more generally, in this situation, we can take C equal Rn. So f is defined on Rn because we are admitting the value plus infinity. So outside C, if C is not the whole of Rn, we extend the function with the value plus infinity. Well, then we say that an element in Rn is a subgradient of f at x bar if for every x in Rn one has this inequality but with x star replacing the gradient. So I'm considering a function which is not necessarily convex, not necessarily continuous, it's an arbitrary function, okay? And then, so at this point, well, this point it will be differentiable, but doesn't matter. I mean, suppose this is the derivative, a line like this, which is below the graph of the function everywhere, but coincides with the function at this point, x star will be the, let's say, the slope of the function. Okay, the vector defining the slopes in every direction. Then we say that it is a subgradient. We are assuming nothing on f. Since we are assuming nothing, we cannot prove anything. In particular, we cannot prove the existence of a subgradient. In this picture, there is a subgradient at this point, but at this point, there is no possible subgradient. There is no line which is below the function everywhere and goes through this point. Okay, but nevertheless, it's convenient to define subgradients for an arbitrary functions because in particular, there is an important class of non-convex functions, it's a large class, popular in optimization, maybe you have heard about it, is the class of DC functions, difference of convex functions. They are non-convex in general. But it's useful to consider the subdifferential of that functions and to give formulas for such a subdifferential which provide optimality conditions. Okay? But I'm giving this definition in general, and but we are going to restrict our attention to the convex case. But even in that general case, we have something very elementary and very useful, that first of all, let me define the subdifferential. Of f at x bar, a set which is denoted like this, subdifferential of f at x bar, is the set of all the subgradients. I have not yet assumed anything on the function f, but I am free to give this definition. I'm defining a set which may be empty, why not? But empty or non-empty, it is always a closed convex set. Because if you look at the condition defining star, this is on X star a linear inequality. So this means that the subdifferential is the solution set of a linear inequality systems with possibly infinitely many inequalities. But it's a closed convex set. So even in general, with no convexity assumption, the subdifferential is a closed convex set, but possibly empty. Okay? Another very general result, which does not require any assumption, any convexity at all. X bar is a global minimum of f if and only if 0 is a subgradient at that point. This is evident. What is the condition of 0 being a subgradient? If 0 is a subgradient, this vanishes. So we get the condition f of x greater than or equal to f of x bar for every x. This is the definition of a global minimum. I have not used any convexity at all. And this simple observation is useful, as I said, for instance, when dealing with DC functions, differences of convex functions. This is an extension of the, as we will see later, of the so-called Fermat's rule, that at the local minimum or maximum, the derivative is equal to 0. Because the subdifferential, the way it is introduced, set of subgradients, is somehow a substitute of the gradient for non-differentiable functions. Okay? Examples. The example everybody cites when introducing the notion of the subdifferential is the absolute, yes, the absolute value function. Okay? This is a convex function, of course, because its epigraph is a convex set, or if you want, because this is the maximum between minus x and x. It's the maximum of two linear functions. Then it is convex. It's the maximum of convex functions. And it's differentiable except at origin. No? When you say, what's the derivative of x, of this absolute value function on x? Well, it is minus 1 if x is negative. No? The slope here is minus 1, is 1 if x is positive, and does not exist at 0. It's undefined. Okay? This is the sine function. Assigned to a number, it's sine plus 1 plus minus 1, depending on whether it is positive or negative. But now let's look at it from the point of view of subgradients. Are there straight lines here through this point which are below the graph of the function? Yes, in fact, there are many. All the straight lines through this point with a slope between -1 and 1. This means the subdifferential of f, the absolute value function at the origin, is the interval -1, 1. Look at the graph of the derivative. -1 here and 1 here, and undefined at 0. But now, if you want the graph not of the derivative, but the graph of the subdifferential, then you are completing the graph of the derivative by adding this interval. Because at 0 it is the interval -1, 1. This addition preserves monotonicity in the sense of set-valued maps, which in this very particular context of one real variable simply means that when you left right, you never go down. You keep horizontally or go up. It's not only monotone in this sense, but it's so-called maximally monotone. Maximally monotone means that you cannot add any point to the graph of this mapping without destroying monotonicity. No matter which point you add, if you are here, then it's no longer monotone because you would go down when moving from to the right from this point, etc. Place the point wherever you like, it will not be monotone. So it's maximally monotone. And it was proved by Rockefeller, who is the leader of complexity. And I hope I'm going to meet him again soon at a conference in Peru. You have also met him a few times, no? Yeah. He's not very young, I would say. He's 90 years old, but traveling a lot and making a lot of research. And so he's planning to go to this conference in Peru, which is going to be held in October. Then, well, one of the many important results obtained by Terry Rockefeller is that subdifferential operators are always maximally monotone. The question is every maximally monotone operator the subdifferential of a convex function? The answer is no. You need an extra property stronger than monotonicity, which is called cyclic monotonicity. Then the answer would be yes. Well, there is a huge theory on monotone operators and maximally monotone operators, which is very beautiful, and with many links to convexity. Once I gave a talk here, long ago, on convex representations of maximally monotone operators. I don't know if you were here on that occasion. Maybe, not sure. Well, but then, so we have a definition. No assumption so far. So it's time to impose some assumptions. Okay? So let us assume that F is convex. And X bar belongs to the interior of the domain of the function. Then, at this point, there is at least a subgradient. The subdifferential is non-empty. I'm going to give a proof of this theorem. Yes, please. No. Absolutely right. I mean, geometrically, supporting hyperplanes and subgradients are the same. But when we talk about subgradient, it's the subgradient of a function. When we talk about the supporting hyperplane is of a set. So you are right, there is an equivalence between supporting hyperplanes to the graph of the epigraph of the function and subgradients. In fact, I was not going to mention this, but since you asked, yeah, this is a very important observation. So I'm not sure if I formally define the notion of the epigraph, so it's time to do so. The epigraph of f, a function defined on Rn, is the set of x alpha in Rn cross R, such that f of x is less than or equal to alpha. Okay, so everything which is above the graph of the function. So it happens that x star belongs to the subdifferential of f at x bar, if and only if x star minus 1, I need an extra variable because the function is in Rn, but the epigraph is in Rn plus 1. So I have to add a new coordinate. Belongs to the normal cone. I have not introduced, and I was not planning to introduce the normal cone. The normal cone to the epigraph at the point x bar, f of x bar. And belonging to the normal cone simply says that the linear function defined by this vector attains a maximum on the epigraph of f at this point. So it defines a supporting hyperplane. That's the equivalence, and this is easy to prove. This is an exercise. If you want, I can give a proof, but as I said, it is an exercise. So this is the normal cone. I'm not going to use normal cone, so I prefer to go back to our previous situation. So, I mean, we need convexity, of course, because I made a picture showing that for a non-convex functions, subgradients may or may not exist, depending on the point you choose. But also, the fact that x bar is in the interior of the effective domain of the function is an essential assumption. Without this assumption, the result would not be true. Example, for one variable, minus the square root of x, which has this graph. Okay? Well, we are always considering functions defined on the whole space. Then this is only defined for x non-negative, but outside the effective domain, it takes the value plus infinity. Then, at the origin, which is in the domain, there is no subgradient, because there is no line through this point, which is below the graph of this function. The only, let's say, supporting hyperplane to the epigraph is the vertical line, but the vertical line does not define an affine function. Okay, and this is because the origin is not in the interior of the domain. So we need this interiority assumption. And this is what I'm going to prove now. And in fact, to make this proof, I'm going to follow your idea about the supporting hyperplane. So I consider the point x bar, f of x bar. X bar is in the domain, so f of x bar is a number. And this is an element belonging to the boundary of the epigraph of f. Okay, it's in the boundary because if we go below f of x bar, we leave the epigraph. Then we are going to use the supporting hyperplane theorem. Maybe you, Vivek, will discuss about it in your second lecture. Supporting hyperplane. So, supporting hyperplane theorem says that if we have a closed convex set and a point in the boundary, there is a supporting hyperplane. It's a hyperplane through the point such that the set is contained in one of the two half spaces defined by the hyperplane. Okay? So, if this is C and this is x bar, and x star is the normal vector to this hyperplane, this property says that there exists x bar such that x star, and there is also a number k such that x star x is less than or equal to k for every x in... No need to mention k here. This should be necessary for the separation theorem, but not so that x star is less than or equal to x star x bar for every x in C. This means that the linear function defined by x star attains its maximum over C at x bar. Okay? One says that x star belongs to the normal cone to C at x bar. Well, then we are going to use the supporting hyperplane theorem in this situation. There exists, but we are in Rn plus 1. So the supporting hyperplane is not defined just by a vector in n, but by a vector in Rn plus 1. So there exists a vector x star alpha in Rn plus 1, such that the linear function it defines on Rn plus 1, so on vectors of the type x alpha, attains its maximum at the boundary point. And this is true for every x alpha in the epigraph of F. Okay? Now, is it okay? Is there any problem? Alpha star is a real number. Thank you. So it defines together with x star, it defines the supporting hyperplane. Good. Then, first observation, we are going to examine this alpha star. So first of all, this alpha star cannot be negative. Do you know why? So this is true for every x alpha in the epigraph, in particular when you take x equal x bar, it is satisfied for every alpha. I'm going to write it. So x star x bar plus alpha star alpha is less than or equal to x star x bar plus alpha star f of x bar. This is a particular case for every alpha greater than or equal to f of x bar, meaning x bar alpha belongs to the epigraph. Okay? This cancels out. So if alpha, I said alpha cannot be negative, alpha cannot be positive. Okay? Alpha cannot be positive. Suppose alpha star is positive. But this holds for every alpha large enough. So make large alpha go to plus infinity, and if alpha star is strictly positive, this should go to plus infinity, which is impossible because there is an upper bound. So alpha star cannot be positive. Must be less than or equal to 0. But I say more. Alpha star cannot be 0. So alpha star must be strictly negative. Do you see a reason why this should be the case? Suppose for a moment that alpha star is equal to 0, then it disappears from this formulation, okay? And then we would have x star x less than or equal to x star x bar for every x alpha, even though alpha doesn't appear here, for every x alpha in the epigraph of f. Is this possible? Why not? Because I observe that alpha does not play any role here, but for every x in the domain of f, you can complete this x with some alpha, f of x, to make it an element of the epigraph. So this should be satisfied for every x in the domain of f. Is this possible? No. But what's the reason why this is impossible? At some moment in the proof, we have to use this assumption that x is in the interior of the domain. Here we are saying that x star defines a supporting a hyperplane at x bar, so x bar cannot be interior, must be on the boundary. At this moment, now I realize, but it can be repaired easily. So let us do it as carefully as possible. So this element, because it defines a hyperplane, cannot be 0. Okay? Which means that either x star is different from 0 or alpha star is different from 0. One of the two, at least, must be different from 0. But would it be possible that x star is equal to 0? Then this inequality would say alpha star alpha less than or equal to alpha star f of x for every x alpha in the epigraph of f. Okay, and Sorry? Thank you. That's important. And then, as this would mean, but now alpha star is different from 0 because the first is equal to 0. Then it's either positive or negative. If it is positive, then alpha would have this upper bound for every x in the domain, for every x alpha in the epigraph of f. If alpha star were negative, then we would have alpha greater than or equal to f of x bar in the epigraph of f. But then, in the first case, because xf of x is in the epigraph, we would have f of x less than or equal to f of x bar for every x in the domain, which means that x bar is a global maximum. But alpha, in fact, has no upper bound. So this is impossible. Alpha making part of a point in the epigraph, there is no upper bound. So this cannot hold. And what about the second situation? In the second case, then, because xf of x is in the epigraph of f, we would have f of x greater than or equal to f of x bar for every x in the domain, which means that x bar is a global minimum. For a global minimum, we know that 0 is a subdifferential, is a subgradient. I wanted to prove the existence of a subgradient, so this case is done. Okay, but this case was missing in the initial proof I was planning. So, the case x star equals 0 we have already solved. So now we assume that x star is different from 0. Okay? But we had first to deal with the case x star equals 0. Then, we interrupted the proof to make this extra at this point, and I said this is impossible for every x in the domain of f because x bar is interior. At an interior point, there cannot be a supporting hyperplane. And this is a real supporting hyperplane because x star is different from 0. If it were possible x star to be equal to 0, 0 or equal to 0 does not contradict anything. Okay, but with x star different from 0, we have an actual supporting hyperplane. And this is impossible. If this supporting hyperplane argument does not like you, then we are at the interior, then consider any direction, and I want to consider the direction of x star. Then if I move in this direction a little bit, following a step small enough, then we are still in the domain. No, because we are very close to x bar. And then this should be satisfied. X star, x bar plus epsilon x star less than or equal to x star x bar. But this simply means that epsilon times the norm of x star to the square is less than or equal to 0, which is impossible because x star is different from 0. So this should be strictly positive. Okay? So now we know that alpha star cannot be 0, should be equal to minus, should be strictly negative. Then I divide all the equation by, all the inequality by alpha star. So I get x star divided by alpha star, x plus alpha greater than or equal to, because alpha star was negative, x star divided by alpha star, x bar plus f of x bar. Okay? Call this vector y star. This inequality is satisfied for every x alpha in the epigraph. In particular, when alpha is equal to f of x, if x is in the domain. We are trying to prove inequality. This inequality is automatically satisfied if x is not in the domain, because in that case f of x is plus infinity. It's greater than or equal to everything. Then, assuming that x is in the domain, then x of x is in the epigraph, and then I have this inequality with alpha equal to f of x. So I have y star x plus f of x greater than or equal to y star x bar plus f of x bar, which means f of x is greater than or equal to minus y star x minus, okay, or let me write it differently, f of x bar plus minus y star y minus y bar x minus, there is no y, x minus x bar. Okay, this is equivalent for every x in the domain. And this simply means that minus y star is a subgradient of f at x bar. So we have been able to prove the existence of a subgradient at this point, but we had to use convexity because we needed the supporting hyperplane theorem, and we had to use that x bar is in the interior of the domain. Again, look at the minus the square root function. There is a supporting hyperplane here, but it's vertical. So it does not define a subgradient, because a subgradient defines the graph of an affine minorant of the function. Okay? So was this proof clear? Now, there is an important connection between subgradients and directional derivatives for convex functions. So from now on, our function is convex, and we will be dealing with a point belonging to the interior of the domain. So I assume f is convex, and x bar is in the interior of the domain of f. I'm going to use the one-sided directional derivatives, which are classical in convex analysis, but it's different as the notion of directional derivative in classical analysis, which is two-sided. So, given a direction D, the directional derivative, one-sided directional derivative of f at x bar in the direction D is defined as the limit as t goes to 0 from the right, so t is positive, of the incremental quotient f of x bar plus td minus f of x bar divided by t. The question is, does this directional derivative exist? Yes. Why? I can give you the details if you want, but I just give you the key ideas. There are two key ideas. If you look at this expression, then you can easily prove, using the algebraic definition of convexity of f, that this depends in an increasing way on t. Okay? Do you want to see it? Or is this... Should I explain this? Okay? I'm not everything about convexity because the topic is subgradients and supergradients. I could have also proved, and I can do it if you like, the equivalence I presented at the beginning for differentiable functions, that the function is convex and only if it's above the tangent hyperplanes. It's not difficult. You will, okay, but you will not include this proof in your tutorial, no? I mean, then suppose t is smaller than t prime, and both are positive. Then I want to prove that f of x plus td minus fx divided by t is less than or equal to the same with t prime instead of t. Okay? I didn't prepare this proof, so excuse me if I cannot do it good enough. And then, if you solve this equation for f of x plus td, this inequality, then you get this is less than or equal to f of x plus t over t prime f of x plus t prime d minus f of x. And this, so x plus td is a convex combination of x and x plus t prime d. No? So x plus td is 1 minus lambda for some lambda which I will compute now. X plus lambda x plus t prime d. What is the lambda? We have to solve this equation for lambda. This x cancels out, and then we get t d equal lambda t prime lambda t prime. I mean, yeah, simply lambda t prime d, no? So easy. So lambda is t divided by t prime. Okay. So I can write this as 1 minus t over t prime x plus t over t prime x plus t. So I write this point as a convex combination of x and x plus t prime d. And then if there is no mistake here and you compute the right hand side, you can write it as 1 minus t over t prime f of x plus t over t prime f of x plus t prime d. Is this correct? This is true because of convexity. F of the convex combination is less than or equal to the corresponding convex combination of the images. So what I said is true. This incremental quotient depends increasingly on t. So the limit exists because it's actually an infimum. So you can write this, if you prefer, as infimum over t positive of f x bar plus td minus f of x bar divided by t. An infimum always exists, so the limit always exists. But an infimum may be minus infinity. And we don't like this. But here it's not minus infinity because we are in the interior of the domain. So I think, I told you that I didn't prepare the proof. I think we can easily prove that this expression is greater than or equal to, thank you, greater than or equal to f of x bar minus epsilon d. I think I can prove this, where epsilon is small enough so that x bar minus epsilon d is still in the domain of f, which is possible because x bar is in the interior of the domain. Is this inequality true? It should also be true as a consequence of convexity again. So let's see what happens. X bar is between x bar plus td and x bar minus epsilon d. This I don't like. No, this is not correct. What is correct is, I think, f of x bar minus f of x bar minus epsilon d divided by epsilon. Something like this should be true. Let us check. If it is not true, I will modify and hopefully in a finite number of steps I will get a correct proof. So if we solve this equation for f of x bar, what do we get? So I don't want to make too many mistakes. So epsilon t f x bar plus td minus epsilon t f of x bar greater than or equal to f of x bar minus f of x bar minus epsilon d. Then 1 minus epsilon over t f of x bar is greater than or equal to this goes to this right, and 2 minus epsilon t sorry? So epsilon, you mean there is a mistake in this inequality? The next line. Should be minus, okay. But then I don't like it either. It's inconvenient. So this means that it may be, I told you that then it should be the opposite. F of x bar minus epsilon d minus f of x bar divided by epsilon. Let's see if it works. Who knows? So for the time being, this is correct, I think. No? Greater than or equal to f of x bar minus epsilon d minus f of x bar, which means 1 minus epsilon over t. F of x bar greater than or equal to epsilon f of x bar minus epsilon d minus epsilon over t f of x bar plus td. It's inconvenient. I should get a plus sign here somewhere. So it doesn't work either, but this should work. Epsilon over t is there a mistake? Here? No. No, because the idea is as follows. So I am comparing, so this is x bar. I am comparing this with what happens on the other side. Okay, so the slope should be increasing. So for a convex function, the slope is always increasing. But what is the slope here? If this is x bar and this is x bar minus epsilon d, the slope is f of x bar minus f of epsilon bar minus epsilon d divided by epsilon. There is a change in signs, but yeah. Okay, so that was the mistake. So let us make a third attempt. Let's see if it works. Now, so this is correct. This term would be with -1 there. So this would be 1 minus epsilon over t, f of x bar, greater than or equal to f of x bar minus f of x bar minus epsilon d. Okay? Now it's correct, I think. And then epsilon over t minus, so this is plus. This is what you mean? No, because, yes. No. Epsilon here I get epsilon over t, so minus plus, this gives minus. And f of x bar also goes with minus. So I think this is correct now. That's absolutely true. Okay. But I don't like this minus sign here. And I don't like this inequality. I should need the opposite inequality. This should be true because this exploits this idea. And x bar is between x bar plus td and x bar minus epsilon d. Okay, do you see any solution to this technical problem? So if not, we postponed this to the next class. I will try to solve this because I mean this didn't make part of the course, but you asked me to give a proof. Okay, and so, but the point is that this is bounded from below. If you believe me that this proof can be repaired, and then the infimum is a finite number, so the one-sided directional derivative always exists. And what we are going to see when we continue, first of all, I will try to repair this proof, but later on, I will show you the strong relationship existing between directional derivatives and subdifferentials. Using the language of convex analysis, but I'm not going to use these ideas in the proof, the directional derivative as a function of the direction is the support function of the subdifferential. Okay, but I'm not going to use this notion. I'm telling you because those of you who are familiar with these ideas may easily understand. Okay, I think it's the time to stop now. No, I think that plus epsilon. No, don't worry. I will think now about this, and I hope I will find a solution. Anyway, it's in the books. One can look at Rockefeller's book or whatever. Mm-hmm.